Good evening, everyone, and thank you once again for joining us for the webinar. So my name is Stalin. Most of you know me, and those who don't know me, I work for Australian PassivHaus Association as advocacy and inside manager. And my job is to make sure all our members get updated with all the Passive House news and updates. So I run monthly this kind of webinar, and you generally get all the invitation from me. So thank you once again for joining us tonight. And today we've got an interesting topic. So we are thrilled to welcome you all to our webinar that aims to shed light on two essential aspects of achieving net zero energy goals. One is electrification and passive house, as the topic is electrification and passive house as pillar of net zero. So this enlightening session will explore into crucial role played by electrification and passive housing in a journey towards sustainable future. In recent year, the urgency to address climate change and reduce carbon emissions has grown exponentially. So as a homeowner, as a passive house, enthusiast or passive house resident of passive houses, most of you are already leading the way in creating environment-friendly living space. However, the path to achieving a net zero carbon footprint require a comprehensive approach that involve both electrification and passive house technique. So today we are lucky to have two distinguished speakers. So I will start introducing with Jeff. So Jeff is an experienced management consultant, strategic relationship leader, and innovative thinker. Over 35 year of career, over a 35-year career, the importance of client service and value has remained central tenets in his every action. As an experienced moderator and presenter, Jeff will probe and explore the opportunity to be efficient, also in parallel retaining an eye on delivering valuable client experience. So Jeff worked for Bridgeford Group, and we have one more speaker, Jordan Lim. So he is a sustainability engineer. So Jordan is passionate about assisting clients reaching their net zero goals with a data-centric approach, and has worked on some landmark residential and commercial projects in Victoria. He has both led and been involved with several council-wide electrification study across Victoria and New South Wales. Jordan previously worked as a solar engineer with experience in designing and bidding for commercial scale solar project up to 25 megawatts. He also has experience in delivering sustainability advice and building energy and sustainability rating across a variety of different project settings, ranging from multi-residential to large commercial development. So during this webinar, we will gain a deeper understanding of the synergy between electrification and passive housing and how they can collectively contribute to achieve net zero target. So our speaker will, both Liam and Jeff, will address common challenges faced in implementing these strategies and provide practical guidance to help all of us to navigate through the transition successfully. So without further ado, I will request Jeff to walk us through the presentation. Jeff and Liam, thank you. And before Jeff, you start, I want to set a bit of a ground rule. So the presentation is around 30 or 40 minutes presentation, and presentation will followed by a Q&A. If you have any question answer, please raise your hand or put a thumb on your chat box and write your question. Then I will ask this on behalf of you to Jeff and Jordan. Yeah, thank you.
Cool. Thank you, Stalin. Welcome, everybody. Firstly, Jordan and I would like to do a welcome to country. So I would like to acknowledge that I am hosting this webinar, or we are hosting this webinar from the lands of both the Bedegal and the Bunurong and Bunawang peoples. I also acknowledge the traditional custodians of the various lands on which all of you work today, and the Aboriginal and Torres Strait Islander people participating in this webinar. So thank you everyone again for your attendance tonight. Jordan and I are really pleased to be here, and we'll hopefully give you something to think about and answer some questions that you may have. The opening remark I will make about these types of presentations from Jordan and members of our team is that, you know, we've got a heavy DNA toward engineers, and therefore it's really difficult to get them to write succinct short statements. They always like to go into rich detail. I'm joking, Jordan. That's not a slap in the face. So that, I guess, lays the groundwork that says that we'll have a lot to cover. We'll endeavour to keep it at a moderate to high level as we go through the presentation, with the view that we'll get some questions that flesh out some detail for you later on near the end of the presentation, as Stalin said. Jordan, if you move the slides forward to just the agenda, please. So for everyone's benefit, I work as a business development executive within the business. So my job is to engage with existing and new clients to help understand opportunities that we can help them with around achieving net zero. So I'll just take you through a bit of background briefly on the Bridgeford Group shortly, and then hand over to Jordan, and he'll take you through what is electrification, take you through a couple of electrification case studies, before covering the topic of synergy between electrification and passive house principles. And then we'll move into a Q&A thereafter. As Stalin said, please stick your hand up at that time and or put the questions in the chat section of the Zoom platform. So if you flick over again, Jordan, the Bridgeford Group, as the title of the slide there denounce, we have a passion and a focus on actionable net zero. So everything that we are delivering to the market, we will only do because it has a link into lowering and or eliminating a carbon emission from a particular enterprise. We work with courageous corporates, public good enterprises, and all three levels of government to achieve this. So we operate across the board. We do tend to operate in the smaller corporate space, but as far as public good enterprises such as water corporations, universities, etc., we operate in whatever sphere they operate in. But we are a multidisciplinary renewable energy, building services, engineering, and energy efficiency consultancy. So our DNA emerged from that building services, electrical engineering, mechanical engineering DNA, and we have morphed ourselves into a highly active bespoke group focusing on delivering actionable net zero results to our clients. So that's my sales spiel. I'm going to leave it there, so in the interest of maximising time for Jordan to get through his material and you guys to ask some questions. So I'll hand over to Jordan now, and look forward to talking to him as we go on.
Jeff, do you also want to talk about just very briefly about the electrification experience that we've done in Victoria, in inner Victoria?
I think I won't talk about it right at this stage. We may come back to that later on. So leave it for the moment and just go on to the electrification. Thanks, Jordan.
Okay, cool. No worries. Hi, everyone. Thanks for being here today. As you guys have heard earlier, I've been involved in several council-wide electrification projects within Victoria. Currently, still also just busy trying to complete several other council-wide electrification studies before the end of financial year. I'm grateful for the opportunity to speak, but I don't claim that I know everything about electrification. But hopefully, if I do my job properly for this presentation, hopefully everyone can take a little bit, can take away a thing or two from this presentation, and hopefully can apply some of the concepts to the work that you are doing. So without further ado, I want to first start with the basics by first defining what is electrification. In raw definition, electrification basically means converting conventional fossil fuel driven technology, like say natural gas, diesel, petrol, or whatnot into electrically powered technology. Now, as Bridgeford Group, most of our work revolves around building services. So, and also because of our passive house audience today, we will be emphasizing more on electrification at the residential and commercial building sectors. So we'll be talking mostly about the removal of natural gas assets only. Before we go on to the measures, I suppose it's important for us to recognize why we at Bridgeford Group think electrification is important. First of all, if the building is electrically powered, there's a potential to reduce your electricity emissions through either installing more renewable systems on site or even just buying renewable power. If they're gas assets, the only way to offset the Scope 1 or Scope 3 emissions is resulted from your diesel or gas assets, basically just buying carbon certificates. Currently, to offset gas emissions on site, it's incredibly challenging because we have to rely on biofuel and hydrogen, which is not necessarily the most simplistic solution ever. Secondly, because you can purchase renewable electricity or install more renewable energy systems on the site, you are reliably offsetting your emissions on the spot. So rather than buying carbon certificates, which we all know, depending on the provider, some has been shown to be unreliable. Third reason would be that there are many efficient electrically powered alternatives out there in the market already. So heat pumps, for example, which we will discuss in later slides. And lastly, because gas assets burn natural gas on site, there will be physical particulate emissions. Electrically powered assets don't have harmful on-site emissions, which is why electric technology has become more favorable over the years. While we think electrification is important, we should also recognize that the grid is currently not entirely renewable energy powered. In fact, if you look at the graph on the left here, with the data sourced from Department of Climate Change, currently natural gas is still a less pollutive source of energy, although at some point, based on federal predictions, our grid will slowly decarbonize over time, and grid electricity will soon be less pollutive than gas. But that's not until quite a few years later. So that's probably one of the main sharings today. I will be sharing some information and data of what we've calculated and also observed over the past year from the electrification measures that have been implemented. So everyone can be better advised on what's actually a good electrification measure from an emissions point of view. Moving on to some of our technology case studies. So we will discuss a few asset categories here. For both domestic and commercial applications, we've got domestic hot water, space heaters, heating hot water, and cooking assets only. And because those are the assets that use natural gas as a source of, because those are just the assets that use natural gas as a source of energy for conventionally designed buildings. Now, for domestic hot water assets, on the left of the screen here, I've provided some gas-fired domestic hot water technology that are quite conventionally applied. You can see that on average, the efficiency is only about 78% to 88%. And the electric alternatives would be either to use electric element heating technology or to use heat pumps. And you can see here, there's actually not much difference, for efficiency gain over electric element heating compared to conventional gas technology. But with heat pump, depending on the refrigerant that is being used, the average efficiency or what we call COP, coefficient of performance, can range from 280% all the way up to 480%. I want to first look at the different kind of performance metrics of electric water heaters compared to conventional gas domestic hot water heaters. On these graphs here on the right, you can see that while electric element heating uses less energy in terms of gigajoule compared to gas domestic hot water system, the emissions outcome, depending on the states that you're in, are not very favorable at all, except if you're from Tasmania. That's because Tasmania has the cleanest electricity supply at this day in time. if we assume a typical, and also if we assume a typical gas rate and electricity rate for residential rates or commercial rates, we are actually paying more for electric element heating than compared to gas domestic hot water. So with these reasons, we at Bridgeford Group don't typically recommend electric element heating for domestic hot water unless the site, can supply solar PV, because otherwise you would just basically be increasing your emissions performance of the building. Or that if you can't install heat pumps at all, because heat pumps does have different kinds of design constraints, we will only then recommend electric element heating as an alternative solution. Heat pump for domestic hot water applications, on the other hand, can save up to 80% in energy. And because of this, it actually have a positive impact in reducing the emissions for domestic hot water systems, because it's just so much more efficient and the operating cost is also less. This does come with a bit of a drawback. It is, however, significantly more expensive than electric element heating. I can't really pull a figure on top of my head, but for systems that can be electrically powered, the same capacity of a system is probably at least 3 or 4 times more expensive. So that's why historically it's not necessarily a very favorable technology. But in this day and time, it's probably a good alternative solution because of rising gas prices. Your operational costs will just keep going, so your payback for the system will just keep getting better and better. But heat pump systems also have to be installed outdoors because heat pump does have a airflow rate requirement. So installing this in new buildings is less of a challenge compared to installing them on existing buildings. Moving on to commercial space heating, you can typically find boiler systems on the left on my screen here in retail spaces, hospitals, or big offices, or even at manufacturing plants. Their efficiency is not very different to the gas-fired domestic hot water system that I've just demonstrated earlier. Although condensing boilers are more efficient than atmospheric boilers, the efficiency is still capped at 96%. It wouldn't go higher than that already. So the heat pump solution for this would be either a commercial scale 2-part heat pump that can be quite big in physical sizes. We'll discuss a little about what the footprint is later. And also modular 2-part heat pumps, which are smaller and applied in apartment buildings in places like Japan. We haven't quite seen a lot of them applied over here in Australia quite yet, but eventually we may find more of them. I thought I should bring up the efficiency curve of heat pumps a little bit, but in case if there are people within this audience that are unaware, heat pumps run best when it's performing on part load. You can see here when it's running on 100%, the efficiency is actually not the best. The COP is only at about 3.5-ish, but this is just an example. It can go all the way up to 4 or maybe even less, 2.8. But this is just an example. When running at 100 capacity, its efficiency is at the worst. But if it's running on part load, the efficiency keeps going up, right? And so for a typical building scenario, if a boiler or a heat pump is sized correctly, we won't actually be seeing the heating system to be running at 100% capacity too much. In fact, most of the time, it's running at capacities lower than 70%, right? And so understanding that historically boiler systems are majestically, one way to describe it would be majestically oversized, which isn't good because there's no value in oversizing boilers. But oversizing heat pumps, in this case, can actually deliver a more energy efficient outcome, right? Because if you oversize it, that means that the likelihood of you running your heat pump system on part load is much higher. But that's not to say that we should oversize heat pump system all we want, right? Just because we happen to have funding. There are diminishing returns to oversizing heat pumps, which we can leave the discussion for a later date. So here's the metrics of a commercial scale 2-part heat pump. So similarly, it's about more than 80% reduction in energy. and it's a measure that can be applied by all states here. You can see here that heat pump technology on a typical scenario can operate with lower emissions compared to well, it seems to be a typo here compared to which it should be a gas boiler instead of gas domestic hot water system, but you guys probably get the gist. From an OPEX point of view, it's great. Although from what I show here, it's nearly half the cost to operate compared to a boiler. Do know that there's a lot of factors that can affect this. Say if you have higher electricity rates because the electrical demand on the site is not addressed properly, or if you happen to have undersized the system and it constantly runs on of peak capacity only where the efficiency is at the worst, the OPEX does go up. But for a well-designed system, the savings can be quite significant. The design considerations for this technology is that it's really big. I don't really have a scalable figure on top of my head, but it's not uncommon to see that these systems, that the systems like heat pump systems like this is probably at least about 3 times higher. So it's like 3 times bigger than a boiler with a similar thermal capacity. Right? So much heavier, much bigger. So structural integrity of the building does need to be addressed to implement this measure. For modular heat pumps, the performance is slightly it's slightly lower, although it's similar, although it's quite similar to a commercial scale 2-part heat pump. It's suitable to, as I mentioned earlier, it's suitable to be used at places like apartments or tall office buildings where there are limited plant space. The footprint is much smaller, a little bit lighter as well, up to 50% smaller, actually 50% smaller, although it is slightly more expensive to implement because of the modularity and with also the better flexibility. The reason why the efficiency is lower for a commercial, compared to a commercial scale heat pump like this one, is because modular heat pumps typically are stacked for its efficiency. So that means that one heat pump will first have to fulfill to its peak capacity, then the second one will start running. So that means that if you have a system where 4 of the modular heat pumps are running at the same time, 3 of them are running at peak capacity. And as we did explain earlier, when heat pumps are running at peak capacity, the efficiency it's at the very lowest. And it's only at the 4th unit, as from my example earlier, which it will be running on part load. That's the reason why efficiency of the overall efficiency of modular 2-part heat pumps are lower than these big units over here. Sorry, moving on, I also want to share a little bit about the findings that we found for 4-pipe heat pump technology, which is a heat pump system that can supply both heating and cooling simultaneously. It can also supply heating only and cooling only as well. So if a development has both boilers and chillers, they can consider using 4-pipe heat pump instead. I won't dive down too much into details of the efficiency of the air-cooled chillers here. It's actually quite similar to the efficiency of the heat pump. That's wide range. So, but for 4-pipe system, it works better if it's on simultaneous heating and cooling. It can go from 350% to 800%. But then again, because of this is the information that I got from a year ago. And every year you have like more efficient systems coming out. So I wouldn't be surprised at all if your overall system, if the overall efficiency that can be achieved by a 4-pipe heat pump can go all the way up to 10.0. Right. So efficiency for running a heating only and cooling only is not as great, right? So that's probably something to take note of. Here are the efficiency curves for a 4-pipe system. If running on cooling or heating only, the efficiency curve is similar to a 2-pipe heat pump. So I probably don't have to share too much on that anymore. But when operating on mixed mode, it's actually better, right, when running on peak load. Right? So this is an example data set that I received from a close heat pump supplier of us. So we've been working with this assumption for a lot of electrification projects. As you can see here, if we maintain a flat cooling load of 100%, but with different scenarios that describes the different part load values and also peak load value for the heating load, you can see that the efficiency of the heat pump is actually quite high when it's running on close to peak conditions. But as one of the heating load or cooling load goes down, the efficiency also drops. And likewise, if both your heating and cooling load, is at the very highest, the efficiency is at the very best, and as it goes down, it also drops. So that's why a system like this, it's best when you apply when this is used as a base load application, and the rest of the heating load and cooling load is being made up by other technology instead. I don't have the metrics, like all these graphs here for a 4-pipe heat pump. But the reason is because the performance of 4-pipe heat pumps differ for different application. It is very situational depending on how much heating or how much cooling is needed. So I don't think it would be fair for me to just make up a scenario and then demonstrate it to you guys. But as I just mentioned earlier, it is extremely good when you apply it on when you can make sure that the system is consistently running at peak heating and peak cooling capacity. So you can see that this system, this type of unit can be applied at, say, aquatic centers, for example, which you would constantly be needing heating for heating. So you will constantly be needing heating for the pools, and then cooling. Let's say if there's got like for aquatic and leisure centers, they've got gyms that constantly need cooling regardless of if it's winter or if it's during summer, because of the human heat load, because of the latent heat that's constantly supplied due to metabolism. The spatial footprint is higher than a typical 2-pipe heat pump model. It is also slightly more costly because of the dual functionality, but as mentioned earlier, it can be really good in certain circumstances. Moving on to space heating technology, I would like to say that electric heaters are not necessarily our favorite, because as you can see here, the efficiency is actually not that, great. There's only there's only on an average 5% increase of efficiency over typical gas-fired heaters. So that's why, if possible, we would typically always like to suggest split systems instead of electrically spaces, because there is a efficiency gain outcome out of this. And so the graphs here kind of show performances that are quite similar to electric domestic hot water systems. There's a slight gain in energy efficiency, but with the emissions performance right now, is actually not amazing. It can still be applied in Tasmania, but there's no reason to do so because of the operating costs. So that's why split systems or maybe even VRFs technologies are a better alternative for us. Moving on, we no longer really see HCV systems anymore, but because of the topic today, because of the audience today, predominantly for PassivHaus, HRVs and ERVs are applied in this manner, right? And again, I don't really have a lot of metrics to supply for this system because HCV operates under gas-fired heating and evaporative cooling. So with evaporative cooling, you don't necessarily consume electricity when you're running cooling, although there's like fans involved, but the cooling comes from water, not necessarily from refrigerants. Whereas for ERV systems or HRV systems that have direct expansion heating and cooling, the heating and cooling does come from an alternative source, like maybe a split systems, maybe a VRF, or maybe a heat pump. So that's why comparing the metrics for an ERV and HRV for a HCV system is not necessarily fair. But I do want to emphasize the efficiency outcome and emissions outcome. So the emissions performance and efficiency performance of our ERV and HRV systems typically better. So I think lastly, what I want to share for space. Well, I think there's another typo error here. It's for gas cooking technology. In case if everyone's not aware, I think I should go through the efficiency for each of these assets here. For gas cooking stove, the efficiency is probably about 33% to 48%, and that's very typical. That's because when you pretty much burn natural gas on the stove here, a lot of the heat has already been dissipated before it reaches your pots or the pots of your pans. So that's why the efficiency is so low. Likewise to barbecue grills and also for gas fryers. Now with electric coil technology, the efficiency is slightly better, although still not as great. So that's why typically induction technology is always the more preferred technology. Now we even have like portable induction. We have portable induction stoves, and also we even have like induction woks already. It always makes me laugh whenever I see a technology like this. I haven't personally worked with this before, but would be interested to see it one day. And so with electric coil technology, as you can see here, it's quite similar. The performance is quite similar if we compare this technology with electric space heaters and electric domestic hot water system. Efficiency gain is not that great. It's only 20% increase, and then the emissions outcome is actually quite terrible. And then OPEX is also really high, and then it's also known to be really slow for heating, so that nobody likes this technology. So typically, we won't recommend this technology at all. That's why we're showing the comparison for induction technology, where it actually saves a lot of energy, and then the emission, although the emissions outcome is not necessarily great, but if we follow the emissions trajectory if we follow the grid decarbonization trajectory predicted by the Department of Climate Change, somewhere around 2030 or 2031, induction technology can be a viable solution from an emissions point of view. And then with the rising gas prices, induction cooking at this day in time, at the moment, induction cooking is slightly more expensive, but with the rising gas prices these days, like this year, the gas contract prices are typically 30% higher than last year already. So if we assume the same trajectory, 30% increase this year, or perhaps 20% increase of gas prices next year, induction cooking technology will be the better solution already by then. And so want to sort of just like briefly touch on the synergy with PassivHaus. I wish I can work on this slide a little bit more, but it's PassivHaus and electrification. The synergy between the two is pretty much that the highly insulated property and also the air tightness and the thermal bridge-free building fabric properties of a PassivHaus, because it reduces the heating and cooling demand of the system. You don't necessarily need to size up your heating and cooling system to be that big. It doesn't need to be, let's say, for a typical uninsulated or poorly insulated building, say, for example, if you have a 1 megawatt heating system or 1 megawatt cooling system, for a PassivHaus, you don't need that big. You probably need like 60% or 50% of it. And then so it then allows you to install a system with a much lower system capacity, and also it's cheaper. It's cheaper, and because heat pump systems that are smaller, that are also less, they're also less as heavy, right? So the structural integrity problems are not as significant, right? And because electrical technology can be supplied via renewable energy, I'm not sure if the PassivHaus certification consider the proportion of renewable energy that is needed to be supplied, but electrification does enable this to happen. Right, and so I think that's pretty much towards the end of this presentation, a little bit quicker than anticipated, but if anyone has any questions, feel free to ask, but hope that this presentation has been helpful.
Yeah, thank you, Jordan. Thank you, Jeff. So we'll open the floor for the question. So if anyone got any question, you can type in the chat box. I can ask that on behalf of you. Okay, we're already getting few. Okay. So I'll start with one. Give me one sec. Okay. So from Cameron, you point out that the part load COP is higher than at full load is, give me a second, my system is playing up. Give me 1 sec. Okay, so you point out that the part load COP is higher than at full load. Is the quoted COP for residential heat pump such a split system at full load? Jordan?
The efficiency for the heat pump systems that I've described in this presentation, they are mostly air to water heat pumps. So for air to water heat pumps, the efficiency curve is like that. It begins at the, so if it's running at 100% capacity, it's really, really low. And so the COP for heat pumps are typically used to size for circuit breakers only. From an electrical engineering point of view, the COP at 100% capacity is important. But from an energy efficiency point of view, we would typically refer to the COPs when it's running a part load. And you can see here is that we don't actually define it by COP. It's actually from NPLV. It's actually net part load value, and the efficiency does increase when the load gets lower. But at some point, you can see that over here, it starts tripping when it goes under 20%. I don't actually have a good reason behind it, but for split systems, for example, the efficiency curve tend to be not as slow. It does go a little bit higher when it's running on part load, but the efficiency curve is a lot more flat than a two-pipe heat pumps.
Very Jordan. Can I just jump in and add to that? It's Cameron here who asked the question. If we look at your standard residential split, is the test standard by which the COP is calculated, is that based on the rated full load of the system?
For a residential split systems?
Yeah,
that's correct.
Okay, thank you.
Yeah, thank you, Cameron. Anyone else? Anyone got any question? Okay, we got one from, a sec. How do you size a system for a home in order to run on part load? This is from Paul.
How do we size a residential? Okay, this is a question that we get asked from, because when we share this knowledge to our client, they get very excited when they say, oh, if the efficiency is so high, why not size up the system such that it only runs at 20% capacity? Well, that's not amazingly, it's not a very reliable solution, because you probably have to oversize your system by 3 times, 4 times, or 5 times in order to achieve a really high part load efficiency. Now, there is a solution the smarter solution to that is probably to install thermal storages, where you can program the thermal storages to kick in when the part load, when the efficiency of the heat pump goes above 30%, and then you can program it in such a way that you don't want the heat pump efficiency to go above 30%, and you want to start sourcing the hot water from your thermal storages. Now, this solution is still currently being explored by heat pump suppliers, because it's never really been done in the past. The only time that this is being done is this is a knowledge that I borrowed from a previous senior engineer of ours, where in Shanghai's cooling demand for some of the council buildings are supplied by chillers, water-cooled chillers that burn in the underground, and so the water-cooled chillers would supply cooling at off-peak hours through a lot of thermal storages underground, right? And then during peak hours, it then supply chilled water. It then supply additional chilled water to supply cooling for the council-wide operation. So even during the day, during the hottest month possible, the system is always running at part load, or it's not even running at all, because it's just running cooling. It's cooling at part load during the night already. And so theoretically, we can apply the solutions. Theoretically, we can apply this kind of a method to residential and commercial systems here. We just need to find a system that can allow for this kind of programming.
So we've got a follow-up question for Paul again. What type of thermal storage are available?
Well, in Bridgeford Group, we don't necessarily endorse a particular brand, but Watermark is pretty good. For Watermark thermal storages are pretty good.
Okay. So question for Tom. Does an oversized HP not tend to cycle on stroke off and impact the COP stroke NPLV?
Sorry, come again. I didn't actually catch the first part of the question.
Does an oversized HP heat pump not tend to cycle on and off and impact the COP stroke NPLV?
Are you concerned? Is the concern about the short cycling of heat pumps?
Tom, if you can ask the question. Tom, you there?
Sure. Sorry, Jordan, to clarify.
Hey, yeah, that's okay.
Your curve reflects a truly oversized heat pump, which may well happen in a passive scenario, where it's able to cycle down to a low point, but invariably it will switch off. And then it will start back up again. And I'm just wondering if that's reflected in that curve that you presented.
Short cycling only happens if you either, like I mentioned earlier, if you majestically oversize a system, that system can keep short cycles within this area. And if you undersize the system, you'll just keep topple off over the 100% load. And so you just have to rely on buffer storage tanks to even enable your system to work. Sorry, did I answer your questions? I may not be getting the question entirely correct.
No, I suppose I was just wondering what happens in the case of a heat pump for space heating that's so oversized that it's always operating right down towards the lowest.
Oh, right down towards
curve.
this. Yeah.
Yes, but actually turning the system off for a time before it then needs to start compressing again.
I haven't really come across with this problem quite yet,
sure.
but it's like we do, like as mechanical engineers, or like as good mechanical engineers, we do try to assume that the system is not oversized to the point where it's always consistently running at 10% load or 20% load only. So the way to sort of mitigate this kind of a scenario would be to not oversize your system by much, and you can do that with proper energy modeling with different softwares available today.
Yeah. Okay. Great. Thanks.
Okay. So we've got a question from John. So, what is the best way to size and deliver hot water to slab heating that is currently served by a gas heater?
Slab heating.
Slab.
Slab heating.
yeah,
like hydronic heating, for example, hydronic slab heating. Yeah. To size them out. Well, I wish my fellow design engineer is here. I am an energy engineer by trade, but to size up the system, well, we Bridgeford Group, we come from a retrofit background. I wonder if you're asking from a retrofit point of view or from a new building point of view, but the way you size up your hydronic heaters and your space heaters wouldn't be too much of a difference, honestly. Like historically, you would have to account for the different types of heat losses from in-floor electric hydronic heaters and also for space heaters. But with heat pumps, the thermal capacity suggested, say again, with any new development these days, you would have to do your Section J assessment. You would have to do your energy modeling anyway, and so the metrics, the energy metrics that you get from as a result from the Section J assessment and also from the thermal energy software would be your best source of information to help you size up for your system.
Thank you. Okay, we've got a few more. So this is from Gerard, does Bridgeford Group provide off-grid solution? This question, or a similar fashion to Skybox by the company Sky Energy?
upgrade solutions. So doing the physical implementation ourselves.
I'll read this back to you. Does Bridgeford Group provide off-grid solution?
Upgrades, so they're here.
Off-grid
solutions. Yeah, we've got several off-grid projects already. Jeff, do you want to sort of share a bit of information with the off-grid projects that we've won over the past few months?
The most significant one, Jordan, that we've won that we're working on currently involves a national park on the southern tip of Victoria, which is off the grid, and they're looking for a sustainable energy ecosystem solution to kind of meet the community's expectation of not burning diesel to support a national park. So in that setting, there's a likely to be a multiple generation solution of wind, pumped hydro and solar to be introduced into that solution down there. That's the most obvious one that we've got hands on at the moment.
Yeah, and if I were to answer some technicalities behind the project for off-grid solutions, it wouldn't work without either a battery or a thermal storage. And then with heat pumps and with cooling and heating, thermal storages is always preferred over a battery. But battery, you would probably want a battery to supply electricity for lighting or for some of the base electrical loads. But for heating and cooling, thermal storages are always preferred, and that's because you can run your heating and cooling systems regardless if there's sunlight or not. You can run your heating and cooling system at part load and then store the heated store the heating hot water and chilled water at the thermal storages already at any time at all.
But few more questions. So this is from Richard. Does the heat load percent COP have implication for the whole of home assessment? Just if anyone on the webinar has information on this, as energy assessor, we have been advised that the thermal performance can assist in determining the size of heat pump. I'm curious if this has been allowed for. This is from Richard. Yeah.
Okay. So correct me if I'm wrong. I believe whole of home is a kind of like a framework or tool that assesses residential buildings. For heat pump scenario, it can be applied for both residential and commercial buildings. In fact, Bridgeford Group had just been engaged to do to sort of provide a methodology or a metric to NATAs to also account for centralized heating systems, and then that would account for centralized heating and cooling systems, and also for single occupancy, what we call SOU, single occupancy unit ratings. And so eventually, let's say next year or the year later, your NATA software for Hero, First Rate, Design Builder, whichever that you're using, would have an additional metric somewhere, whether or not in the form of a report or in the form of additional icon somewhere in the software that rates how well a system, how well a heat pump system, or maybe even an air source, how well a heat pump system is running, or even your VRVs or your split systems running. So that will come eventually. We are engaged to do a study this year, and then NATAs and Department of Climate Change does have plan to start integrating this into the software already by early next year or mid next year if things goes to plan.
Any other question? We got a few more minutes. Any last few questions? Anyone? Okay. I will just yeah. Okay. I'll just quickly go through this one if I missed anyone. Okay. Now all good for timing then. I think everyone asked their question. So just double check this. Second. Okay, so I think we'll wrap the webinar now.
Sure.
Thank you once again, everyone, and thank you, Jeff. Thank you, Jordan, for walking us through this beautiful presentation. And this recording is going to be available to all the participants and member. And if you have any question, please send us an email. We can share with Jeff and Jordan, or if you want to contact them, their email address on the screen. So if you have any question, you can directly drop them email as well.
Yeah.
Thank you. And
I got I do encourage everyone to, like, if there are questions, please do shoot us an email. Like, we'd like to discuss about topics like this, because again, we don't claim to know everything, and then sometimes we discover new problems and new issues as we go. Sometimes we may overlook something as we're being the person, being the guys running the field. Sometimes we overlook something that's not looked from the user's point of view, or even we do need that. That's why design reviews happens. And so if anyone has got questions, please let us know, shoot us an email. We're happy to engage in a discussion afterwards.
Thank you, and everyone enjoy your rest of the evening. Thank you. Bye-bye.
Thanks, Alan. Thanks, everyone.
Bye.
Thanks, everyone.
Bye.